Hello students, this is the recording that goes over the first half of the chemistry final exam. So taking a look here, we're going to take a look at classifying matter first. And so remember that we learned about four different things. We learned about elements, compounds, homogeneous mixtures, and heterogeneous mixtures. And we were able to differentiate between these things based on a few characteristics. So first off, taking a look over here on the left-hand side, elements and compounds are both pure substances, which means that they cannot be separated physically. So if you take a look right here at the question, can it be separated physically? The answer is no, and so that is why it is a pure substance. Taking a look over here then, homogeneous and heterogeneous mixtures are both mixtures, meaning that they can be separated physically, right? So you can see these both fall under yes, they can be physically separated. So that's the first thing that you need to know. Elements and compounds are both pure. Mixtures can be separated physically, right? That's the main idea here. Now, to differentiate between them within their individual kind of groups, so taking a look here, elements right here cannot be separated chemically, meaning that elements only are made up of one type of atom. One type of atom, and so you can't make it any simpler than what it already chemically is. Oxygen will remain oxygen and gold will remain gold. You can see those examples down here. These are also all things that are found on the periodic table. So if you find them on the periodic table, like gold is Au, oxygen is O, that is a big indicator that it is an element. Compounds, on the other hand, again, are still pure physically. You can't physically separate a compound, but they can be separated chemically by undergoing chemical reactions, which we've learned about. But compounds here are going to be made up of more than one type of atom. And so we have some examples here, right? So we have water, which is H2O, made up of 2 hydrogens, 1 oxygen, and carbon dioxide, CO2, made up of 1 carbon, 2 oxygens. So obviously, again, we can see those letters are involved, but this time there's more than one type. All right, there's both a hydrogen and an oxygen, or both a carbon and oxygens here. Okay, so those are going to be our definitions for elements and compounds. Moving over here towards mixtures, back to mixtures here. Again, can be separated physically, but there are two different types. So the first type is homogeneous. The prefix right here, homo, means it looks the same, right? So same, that's what that prefix means. And so taking a look here, homogeneous mixtures, yes. The question is it uniform? Yes, uniform meaning the same. So it looks the same throughout. So the same, or I can say uniform, kind of like perfectly blended together. And examples here would be salt dissolved into water and sugar dissolved into water, both of which dissolve completely so that you can't actually see any salt or any sugar left over. Can't see any leftover particles. So it looks exactly the same. It's completely blended. If you took a sample of sugar water from the top of a cup versus the bottom of a cup versus the middle of a cup, they would all taste and look identical. Completely uniform, completely the same. Heterogeneous mixtures, on the other hand, have distinct components that you can actually see the differences. All right, so these are not uniform. They have distinct parts that you can see. Okay, so examples here would be like how rocks can be made up of different minerals, and if you were to break apart a rock, you could actually see those minerals. Same thing with wood. You can see different particles in wood. Even paper and steel are not completely uniform. You can still see different particles, different parts, right? So other examples here would be like most types of food, right? So if you think about like cookies, or if you think about ramen, all of those things have different parts, right? Cookies, you can very clearly see the chocolate chips versus the top and the bottom. One side might be more burned, the one side might be softer. Same thing with ramen. You can very clearly see noodles versus the soup versus the broth. And even within that broth, you can see different seasonings. You can see some of the herbs that are left over. So they don't look uniform. If I take a sample from one side versus the other side, I might get different amounts of noodles or soup, different amounts of chocolate chips, or burnt parts or soft parts, so it all looks different. Every sample would be different. Just a reminder here that hetero, that prefix means different, so that's a pretty good indicator that is talking about differences. All right, so that should help us out with the first question. So I'm going to go ahead and clear this out, and let's go ahead and talk a little bit about the question. So taking a look here, the question says, match the following terms to their best definitions and examples. So you can see here that there are 4 definitions and there are 4 examples. Okay, so, and these are your options, so each option will end up being matched up with 2 things, a definition and an example. All right, so taking a look here, we're looking at things that are separated physically and do not look uniform throughout. Yours will probably be scrambled, so make sure you read carefully. Salt, you can see, has Na, which is sodium, and Cl, chlorine. Remember, the chemical name for salt is sodium chloride. So that should help you figure out whether or not that's an example of an element, compound, heterogeneous, or homogeneous mixture. Sugar being dissolved in water, again, gets completely dissolved, and so every sample is identical or uniform, so that should help you figure out what that is. Pizza, again, looks very different throughout, right? So you have different, each sample looks different. So for example, one slice might have more pepperoni and one slice might have more cheese. So that should help you figure out what that is an example of. Something that is physically pure, all right, but is made up of only one type of atom. Remember, if you need help on this, you can just look up which of our, when we go to look for the example, you can look up, right, what on the periodic table, right? If something is on the periodic table of elements, it's called the periodic table of elements, therefore it is an element. So that's just a hint for talking about the examples. So made up of one type of atom, you need to figure out what that is, element, compound, or a type of mixture. Nitrogen, you can see here, is abbreviated as a capital N. Can be physically separated, again, so we can see the separation happening, and this time it does look uniform throughout. So that'll be important for differentiating. And finally, something that's physically pure but is actually made up of more than one type of atom. All right, so again, just go back to what we learned, and if you need more help on that, you can always rewind, pause, and then maybe just do each one at a time until you have them all matched up correctly. Go ahead, pause the video, and then continue playing when you're ready. All right, so let's talk a little bit about phase changes for our next question. So phase changes we learned are when we go from one state to a different state. The states that we talked about a lot were solid, liquid, and gas. So taking a look here, we learned about about melting, which is where we go from a solid to a liquid. Remember, solids are very rigid, like ice, for example. And liquids are going to flow like liquid water. Okay. And then the reverse, if I go from a liquid to a solid, that would be freezing, right? Turning it back into ice. Vaporization is where I go from a liquid to a gas. Liquids, again, like liquid water, when it is boiled or when it's evaporated, will turn into steam or gas, right? Gaseous water. So that's vaporization. You can see the word vapor in it. Condensation is the reverse, where you go from a gas to a liquid. This usually happens when the gas gets really cold. Like, so for example, outside on a hot day, the gas is very hot. So here's my hot gas. But if I have a cold drink, right, here, then that gas is going to go ahead and come over to this cold drink, and as it cools down, it's going to turn back into a liquid, which is why you get liquid drops on the outside of your cup. That is called condensation. All right, sublimation we learned is when we go directly from a solid to a gas. Example that you can see right here is dry ice, which is solid CO2 that is turning into gaseous CO2. You can see that gas coming off. And that happens when it gets hot really fast, right? Where the temperature increases so quickly that it actually skips the liquid phase. And then the reverse would then be gas to solid, deposition. Example here would be like frost, when it gets really, really cold very rapidly, and the gas from the atmosphere, again, we have gaseous water in our atmosphere, will actually freeze onto plants or grass and will deposit there as frost, as ice. All right, so that would be the opposite. So those are the actual phase changes. Let's go ahead and talk about some of the characteristics that are happening during those phase changes. So remember that different phase changes are either endothermic or exothermic. And what this has to do with is it's explaining to you what's happening to temperature, what's happening to the motion of the particles, and what's happening to heat. Okay? So taking a look here, endothermic, the word endo, all right, looks a lot like the word enter. So this means that heat is going into the substance. So heat is going into the substance. And so if we take a look here, that means that that substance is going to be absorbing that thermal energy, that heat. And as that heat goes into it, it's going to make it hotter and hotter. Obviously, right? If heat's going into a substance, it gets hotter and hotter. It increases the temperature, right? And as it increases the temperature, this is important to understand that heat is just a type of energy, right? We talked about heat and thermal energy are kind of synonyms here. So it's just energy, and so as it increases the temperature, gets hotter and hotter, gets more and more heat energy, then the particles have more energy, and so they will begin to move faster. So in both of these instances on top here, these are going to both be examples of endothermic processes. So melting and evaporation are always endothermic processes. Again, the reason is because they're getting extra heat, right? Heat is entering, we're adding energy to the substance, and it's going to increase the temperature, get hotter and hotter, right? Liquid water is going to be hotter than ice. Gaseous water, water vapor is going to be hotter than liquid water. And those particles will also begin to move faster, which is why ice is very rigid and doesn't move. Water flows, and then water vapor moves very chaotically and rapidly. Gases move very rapidly. Okay, so these are all examples of endothermic processes. So we now understand their definitions as well as why these happen. Exothermic, the prefix right here, exo, means that heat exits. And so as heat exits, that means it's actually losing heat, right? So the substance will be losing heat, or heat is being released, okay? And the result is if you're losing heat, heat's exiting, heat's being released, then in that case, the substance will actually decrease the temperature. So the substance will get colder. All right, so that's going to happen in things like freezing and condensation. Again, we talked about how freezing, turning liquid water into ice, obviously it needs to go into a cold, it's going to get colder. Ice is going to be colder. And same thing, condensation we talked about happens outside when water vapor condenses onto a cold drink because it's cooling down. So it's getting colder, it's turning into a liquid. Now again, the reverse is going to happen here. If the temperature is decreasing, it's losing heat, which is a type of energy, then that means our particles are losing energy. So they're losing energy. And in that case, that results in our particles moving much slower, which again makes a lot of sense because we have our particles first moving very rapidly, then they begin to lose heat, they lose energy, and so they are no longer as chaotic. They turn back into a liquid. They can still flow, so they have some energy. And then turning even colder, losing even more heat and energy, they become they begin to move very, very slowly. They lose a lot of motion, and they are losing and they begin to just kind of vibrate in place. They don't flow anymore, they aren't chaotic. So right here, they're moving much, much slower, which is why ice doesn't flow. Ice is very solid, ice is very rigid. All right, so that's going to be the other two types here. And obviously, we can talk about the other ones, right? So going directly from ice, from solid to gas, remember we talked about, was sublimation, whereas going directly from gas back into a solid was deposition, okay? But for your questions today, we're really only going to be looking at these four right here. All right, so let's go ahead and now take a look at the actual question. All right, so everybody has a different question, so make sure you read yours carefully. It says that you have either a solid, gas, or liquid, and it turns into a different phase, a different solid, gas, or liquid. So the question is, what type of phase change is this? That should be really easy for you to identify. We just talked about this on this slide right here, so that should be super easy to identify. Then from there, you should be able to also identify these things, right? You should be able to then identify this stuff, which is what's happening to temperature, are the particles moving faster or slower, and is heat entering, making it endothermic, or is heat exiting, making it exothermic? All right, so taking a look here, you will have 4 answers, right? So you can see here's your options for A, here's your options for B, C, and D. So again, for these parts, just once you know your phase change, you should be able to kind of observe what's happening here. So you should be able to reason out, am I getting hotter? Is temperature increasing and therefore moving faster? And so in order to get hotter and move faster, I need to have heat added, so heat enters. Or is temperature decreasing? Right, temperature is decreasing, particles are getting slower, and in that case, do I need to lose energy? And heat has to exit, making it exothermic. All right, so that is going to be question number 2. Make sure you pause the video and continue playing when you're ready. All right, so let's go ahead and take a look at questions 3 and 4. So 3 and 4 look very similar to each other. So the question says that you have a certain number of protons, neutrons, and electrons. Again, everybody will have different amounts. So the question is, what is the identity of the atom? Then it asks you to calculate atomic mass, calculate the overall charge, and then based on its charge, determine if it's an anion or a cation. All right, so what you need to know here is that, remember, that identity of an atom is based on its number of protons, which is also the atomic number, which is the number at the top of the element's square. Okay, so that being said, in order to do this, in order to figure out the identity, all you need to look at is how many protons does it have, and then look at the periodic table. So as always, I highly recommend that you are using ptable.com. And let me go ahead and show you what that looks like right here. Oh, sorry. There we go. All right, so taking a look right here. So for example, if you have osmium, for example, osmium has an atomic number at the top of 76, right? So 76 is the atomic number, which is also the number of protons. So again, if it's asking you what's the identity of something, you just look at what's the number of protons, and then find that number at the top, and that number at the top will tell you exactly what element it is. So for example, again, this would be just an example, this is not real, but if I had 76 protons, right, then in that case I would look for 76 at the top of a square and say, oh, 76 osmium, obviously has to be osmium. Again, this is just an example. Example, do not copy. Okay. So extremely important, please do not copy, because this has nothing to do with yours. All right, so let's go ahead and jump back over to our question here. Oops, here we go. All right, so let's go ahead and take a look at our question here. I'm going to go ahead and just erase some of this stuff. Good. Okay. So then it asks, what's the atomic mass of the atom? This is really easy. Remember that in an atom, only protons and neutrons have substantial mass. Remember, electrons are super tiny, and so we don't consider electrons to be a part of the atomic mass. We can ignore them. They're very, very, very tiny. So that being said, taking a look here, atomic mass is then all you need to do is add up the number of protons and neutrons that you have. Each proton, right? Each proton weighs an AMU, atomic mass unit, and each neutron weighs an AMU, an atomic mass unit. So if you just add up all the protons, add up all the neutrons, that will give you your atomic mass, and the units here should be in AMUs, atomic mass units. Okay? Now for the overall charge of the atom, charge has to do with things that have charge. Now taking a look here, protons have a +1 charge. Neutrons have 0 charge, they are neutral. And electrons have a -1 charge. Okay, so based on this right here, okay, we can ignore neutrons. All right, so when we're calculating charge, you can ignore neutrons because neutrons have 0 charge. So instead, all we're going to go ahead and do for calculating charge is we're going to take the charge of the protons plus the charge of the electrons. But what you'll notice here is that protons you can leave as like a normal positive number because again protons are positive. So however many protons you have, that's the number that you should put in here, right? Positive charge here. Okay, electrons on the other hand, we said are negatively charged. So you actually take this number right here and we have to make sure that it's actually negative. All right, so that's why you can see, let me get a different color here. That's why you can see right here, I put that there's a negative sign in front. All right, so when you plug this into your calculator, you're going to either have to add a negative, or remember that when you add a negative, that's actually the same as subtracting. So if you want to plug this into your calculator, you can actually just put a minus sign. So you could take your number of protons minus your number of electrons. Okay, so that'll give you your charge. Make sure you do that very carefully because you could end up with an overall positive charge or an overall negative charge. And that being said, that brings us to our last question. So if you do end up with an overall negative charge, remember that a negative ion is going to be what we call an anion. Remember this N right here meaning like negative. And if you end up with a positive answer up here, positive answer, then that would make it a cation, which is a positive type of ion, has a positive charge. And again, the way I remember that is the letter T looks like a plus sign. Okay, so that should help you answer question 3, part A, B, C, and D. Pause the video and continue playing when you're ready. This is actually also, again, exactly how you will do question 4 as well. All right, so let's go ahead and talk a little bit about valence electrons. Remember that atoms have electrons that are on the outside of the atom. Now, most atoms want to have 8 valence electrons on their outermost shell. The outermost shell, in this case here, being the blue shell. So when we talk about valence electrons, which is how atoms bond, we ignore everything in the middle. So you can ignore everything. Sorry, let me get different colors. So you can ignore everything in the center here. We only care about this outermost shell, the outside one. So again, you can ignore everything in the center. We don't care about any of that. Okay, so anyways, that being said, so again, on this outermost shell, most atoms want to have 8 valence electrons. And they'll either gain electrons through bonding to fill up that valence shell, or they will try to lose electrons and give them away to drop down to a shell that's already full, because all the shells underneath, like these ones, will already have been filled up. So sometimes atoms will try to lose all these electrons so that they can drop down to a shell that's already full. So we're going to talk about that in just a moment. But again, atoms will gain or lose depending on trying to fill their shells. All right, so let's go ahead and talk a little bit about that. So metals are going to lose electrons. On our periodic table, metals are the ones that are on the leftish side. So you can see here are all the metals. Everything in these colors are going to be metals on the periodic table. And all of these metals have 1 to 3 valence electrons. Now remember that the octet rule is that they want 8 valence electrons. So in this case, all right, for metals only have 1 to 3 valence electrons. So instead of trying to gain a whole bunch more, for example, if you have 1 valence electron, you would have to gain 7 more to get to 8. Instead of trying to gain electrons, they prefer to just lose them, right? So they only have a few valence electrons, And so they're just going to go ahead and try to lose them because that's going to be easier for them. And by losing them, they just drop down to a shell that's already full. So when metals bond, they give away, they lose their electrons, they send them off to somebody else, and that way they can drop down to a shell that's already full, and now they're happy. Okay, now nonmetals on the other hand are on the right hand side. So you can see nonmetals are going to be in green and this like purplish pinkish color over here. Nonmetals on the other hand are the opposite. So nonmetals already have most of their electrons, right? So this is most of their valence electrons, their outermost electrons. And so they're really close to getting to 8, to that octet rule up here. So for example, if you have 7 valence electrons, you just need 1 more. And so when bonding, nonmetals will absolutely gain electrons. They're going to go ahead and try to take electrons because, again, they're really close to having a complete valence shell. So just by getting a few extra, now they're happy and awesome. All right, so all these nonmetals over here on the right are generally going to want to gain electrons. Now, the periodic table is actually really useful here because the periodic table is actually organized by the number of valence electrons that you have, and that has to do with group numbers. So these group numbers you can see here at the top. All right, so taking a look here, the top numbers, sorry, let me make this a little bit smaller so that I can fit it all on here. Okay, so the top number of the column is the group number, okay? And the group number is super useful because, again, the periodic table is intentionally organized so that the groups are the number of valence electrons that an atom has. So taking a look here, if you have 1 valence electron, then you are in group 1. If you have 2 valence electrons, then you are in group 2. Now, we kind of ignore the middle for high school chemistry because the middle transition metals act kind of weird, okay? But moving over to the other side, group 13, again, these, you don't count it as 13 valence electrons. Instead, you only look at the last digit of the column. So in this case, group 13 has 3 valence electrons. So if you see 3 valence electrons, you know it must be in group 13. If you see 4 valence electrons, it must be in group 14. 5 is group 15. 6 valence electrons is group 16, 17, and 18. Just keep on going. Group 18 has 8 valence electrons. All right, and again, that should help you identify, what group is it in? And again, is it probably going to be a metal where it only has a few, 1, 2, or 3 valence electrons that it wants to lose? Or is it going to be a nonmetal having 5, 6, or 7 valence electrons where it wants to gain electrons? All right, so at this point, we should be able to do the next few questions. So let's go ahead and take a look at this. This is going to be questions 5 and 6. So you have a Bohr model up here, which everybody has a different Bohr model. Bohr models look like this. So in case you're wondering right now what this picture should look like. But again, for the Bohr model, you need to ignore everything in the center and only look at the outermost shell ring, okay? So you should only, again, be looking at this outermost shell. Again, ignore every other shell, ignore the nucleus, ignore the smaller shells. Only look at the outermost shell, okay? Now, so based on that, you should be able to count up the number of valence electrons. So count the valence electrons that are only on the outermost shell. Again, do not count any valence electrons that are on inner shells. Okay, do not count any electrons that are on inner shells. So based on this, you should be able to identify, will the atom prefer to gain or lose electrons? Remember, if it only has a few, meaning you only count 1 to 3 on the outermost shell, it'll prefer to lose electrons. If you count up 5 to 7 on the outermost shell, that means it has most of its octet. It just needs a few more, so it's going to prefer to gain electrons. Then taking a look here, what group will it be in? We just went over that, right? So we know all of the number of sorry, we know all of the number of valence electrons and their groups. So this is kind of just a reference that you need to have memorized. Again, looking at the last number, that always tells you the group and the valence electrons, okay? So there we go. So that'll help you with your group. Again, group is just the last number of the group, the last digit, I should say, the last digit, or the ending digit. The ending digit of the group number is the same as the valence electrons. So my example here is that, right, group 14, or sorry, so if you have 4 valence electrons, then you would, for example, be in group 14, okay? This is just an example, do not copy. I know nobody has a group 14, okay? So taking a look here again, yeah, that last digit right here, group 4, 14, 4 valence electrons. Group 14, 4 valence electrons, okay? And then therefore, will this element most likely be a metal, non-metal, or metalloid? Again, we just went over that. If you are over here on the left-hand side with 1 to 3 valence electrons, that means you're in groups 1, 2, or 13. Sorry, let me clear this out. That means you're in groups 1, 2, or 13. Then you will most likely be a metal. If you are in groups 5, 6, and 7, then that will most likely make you a non-metal. There are metalloids, but for your example, I know nobody has a metalloid, so you don't need to worry about that. That's just a helpful hint because you're watching the recording. So let's go ahead and keep on moving. Again, that should help you identify metal or non-metal. So again, if it gains, it's a non-metal. If it loses, it's a metal. Okay? All right, let's go ahead and keep on moving. Pause the video and continue playing when you're ready. All right, so the next couple questions have to do with electronegativity. Remember, the electronegativity is the ability to attract electrons. All right, so the ability to attract negative electrons. Okay? Now, the thing is that the smaller an atom is, the better it is at being able to attract electrons. Think about how a small hand can reach out and grab something more easily than a larger hand. Like a kid can get into smaller spaces than an adult. But we kind of talked about this, that the smaller they are, the easier it is for the nucleus, which is what is attracting the electrons, to reach outside of itself and grab new electrons. Okay, so taking a look here, we talked about both electronegativity in groups and in rows. In periods. So in periods, which are the rows going from left to right, so from like this, for example, right? So from left to right, as you go towards the right, your electronegativity actually increases. So the further you are to the right, the higher your electronegativity, whereas at the left side, much lower. Now the reason for this is because everybody in the same row has the same valence shell. All right, they all look identical in terms of their valence shells. So for example, here, let me actually take a look here at this row right here. So this is this period, okay? So for example, carbon and nitrogen are both in the same period, and they're specifically in the second period, the second row, and so they both have 2 shells, right? So you can see right here that carbon has 1, 2 green shells here, and nitrogen has 1, 2 green shells right here. So what that means is that as you move more towards the right in a row, you have the same exact structure, the same valence shells. However, you are adding protons. Remember that the number at the top tells you the number of protons. So I start out with 3 protons, 4 protons, 5, and now you can see carbon has 6 protons right here, whereas nitrogen has 7 protons right here. So as you add more and more protons, protons are positively charged, and remember electrons are negatively, right? So negative electrons, and we've got positive protons, okay? And those are the things that are actually attracting those electrons. So the more protons you have, the more attractive you are. So taking a look here, as we move to the right in a row, nitrogen has more protons, it has 7, and so it is more attractive 2 electrons than carbon. And so what it's going to do is it's actually going to pull in all of its electrons because it's more attractive, it's cuter, it's got more protons, more positives. And so it's going to pull in those shells and it's going to be really good at attracting electrons. So it'll both get smaller and be easier to reach new electrons, as well as it just has more protons to attract electrons. Okay, now the exception here is noble gases, which are group 18 all the way over here on the right. So these ones right here. Remember, noble gases already have completely full valences. They have all 8 of their electrons. Group 18 has 8 valence electrons. That is a full octet. So those ones are actually not electronegative at all. So we just ignore noble gases. All right, so anyways, taking a look here though, what this means is that basically this group, so basically as we move more and more towards the right, the more electronegative we get. So within period 2, fluorine will be more electronegative. Within period 3, chlorine will be more electronegative. Period 4, bromine will be more electronegative, and so on and so forth. Now let's go ahead and talk a little bit about what's going on in our groups. So in our groups, this has to do again with the size of the atoms. Okay, so taking a look at a group, so for example in this one I'm taking a look at this group right here. Okay, so in group 1, remember that atoms have different number of shells. So as you move down, they have more and more shells, because remember, shells are related to the period. So lithium's in the second row, it only has 2 shells. Sodium's in the third row or period, it has 3 shells. Potassium's in the fourth row or period, it has 4 shells. And you can see those right here. So lithium only has 2 shells, sodium has 3, and potassium has 4. So again, the smaller you are, the more electronegative you are. And so lithium right here is actually going to be a lot more electronegative. And the reason for that is because it's much smaller. It has less shells, it's easier for it to reach new electrons. And it doesn't have to move past a whole bunch of stuff, right? So here, down here, potassium has to try to get its protons to attract an electron through a whole bunch of shells, which is really difficult. So again, the smaller you are, the more electronegative you are. So that means that in group 1, lithium's more electronegative, beryllium's more electronegative, boron and carbon and nitrogen and oxygen and fluorine. All of these are a lot more electronegative because they're at the top of our periodic table. And again, we ignore the noble gases. So again, the main idea here is that you will be highest to the right in a period or row, okay? And you will also be highest towards the top in a group, which is a column, okay, towards the top. All right, so that should help you figure out these next few questions. So taking a look here, you can see question number 7 asks about the electronegativity within a group. And again, we said that electronegativity is going to be higher towards the top of the group. All right, towards the top of the group. And again, that has to do with the fact that it's smaller, right? It has less shells, and therefore it's easier to reach new electrons. Okay, so that should help you with question number 7. Make sure you read the explanations correctly, because the explanations might look right, but if you don't read the whole explanation, you will get it wrong. So read the entire explanation and make sure it is 100% true, okay, because there are tricky parts, all right? There are tricky explanations, okay? All right, so that'll help you with this one. Pause the video and then continue playing when you're ready. All right, so let's go ahead and take a look at question number 8 then. Question number 8 is then going to be taking a look at the period. And remember, we said that as we move towards the right, that is when our electronegativity increases, right? And the reason for that is because, again, we have more protons pulling in the same electron shell, which makes it smaller, and now it's easier to reach new electrons. Okay, the smaller you are, the easier it is to reach. So that should help you both identify which one has the highest electronegativity. Again, we want to move more towards the right, and make sure, again, that you read the actual explanation. All right, read it and make sure it is 100% true. True. There we go. And I just want to remind you that we don't include noble gases, but in these instances, there are no noble gases provided. So you don't have to worry about noble gases in either question 7 or question 8. It's just look towards the top and look towards the right. All right, so that's the first half of our exam. Thank you so much for working on this, and then we will continue working on part 2 later. Thank you.